in this session, I'm going to talk to you about probe designs. And before we go ahead, I could just go over this. What?
Remember to protect your voice.
Okay. So before we go ahead, I'll go over the schematic of how the in situ probes are designed and how they work. So this is your target mRNA, and you design a set of probes, basically a left set of hybridization probes and a right set of hybridization probes. So these are the probes that you're going to learn design now. So these probes are really long oligos, which have a small portion that's complementary to your mRNA, and this part, which is like just going to be like freely floating until you add the bridge and the circle. So the bridge has regions that are complementary to a part of the H probe arm, which you can see here and here. And the circles are going to have regions that are complementary to the rest of the H probe arms on either sides. So once you're done, so the first hybridization would be just with the H probes. Then you would add the bridge and the circle. Again, the bridge and circle are linear oligos that you order them as standard oligos from IDT. The only difference between these guys and the H probes is that you will order these in like a slightly better quality, like you would preferably go for like an HPLC purification. And the reason why you need to do that is you want to eventually phosphorylate them. So these oligos are just sold as like standard primary kind of oligos. They don't have a phosphorylation site on their 5' end, and you need that if you are going to ligate it. So you would order them as high quality oligos from IDT, and you will set up a phosphorylation reaction using this enzyme polynucleotide kinase. So the handout has like all the details on how you have to set up the reaction. So you would phosphorylate the 5' ends before, and you would do this before you start your in situ. So that like once you get your oligos, you can like set up a phosphorylation reaction, and you can freeze this at -20, and you can use it like for multiple rounds of in situs. And so, okay, once you've added the phosphorylated oligos, they would bind, and then you would set up your ligation reaction, which would basically close the circle. And then you would add the 529 polymerase, which would make multiple copies of this circle. And the circle itself has regions which are complementary to a detection oligo. So detection oligos are like usual oligos to which a fluorophore is attached to the 5' end. So the circle has like regions which are complementary to it. So when you make multiple copies of the circle, you can see that these target oligo sites are also like spread across the amplicon. And when you add the detection probe, it can bind to multiple such sites. So the example here shows just one oligo bound to one target site, but ideally it would just basically like bind everywhere along the amplicon. And you would see all of this as one big puncture. Okay, so if you look at your handout, so the first part says label probes are detection probes. So these are basically, these guys. So this is going to be, so what I've given here is just an oligo sequence. So you can just go to IDT and order the preferred fluorophore combination, and you can ask them to attach it to the 5' end. Yeah. And again, these oligos, you would order them with HPLC purification, like basically high quality oligos. And I think you're good for Sci-Fi, 488, Sci3, and Texas Red. IDT does not sell oligos for the 405 range, basically the one that you would use instead of DAPI, the 5th channel. So you have to like buy the diester and conjugate it to the oligo yourself. So the information is like given under that. So this is something that you would order. Then the circle components. So CC is connector circle, which is basically this one. And CB is the common bridge. So the bridge is going to be used for all experiments, irrespective of what fluorophore you use. The circle is going to depend on what fluorophore readout you're interested in using. Okay. So we already have designed the bridge and the circle, so you have the sequences here. So you can just use these sequences and order them, so you don't have to like design new circles or bridges. And these you would again order as high quality oligos, and once you get them, you will set up a phosphorylation reaction, and you can basically store this at -20 and keep using it for several in situs. Okay, so this part is done. So you know how to get your label probes, you know the bridge and the circle sequences and how to do them. The part where you need to like design individually are the edge probes, because these are going to depend on what target mRNA you're interested and what fluorophore you want to work with. So we were thinking of like basically going over the entire probe design, like pick a gene and see how you can design like a set of probes. So I can basically show you guys here. Does it not project to that page?
I can make it mirror.
Mirror? Yeah. So we already have the steps listed out here. We can just go over the entire sequence and try designing a probe set for like one gene. Thanks. Okay, so the first thing is once you know, is it good?
Yeah. Mm-hmm.
Okay, yeah. So the first thing is once you know this is your target gene, you will want to find the sequence. So go to NCBI, go to nucleotide. In my case, I'm taking FGF10. So you can specify whether you want mouse or human. So you want, so we usually prefer like it depends on your purpose, like what you are interested in looking at. But usually, I just take the sequence which I think is like complete, not a partial series or. Okay, so you have the sequence here, and so I'm just gonna copy. I'm just going to copy the whole sequence and paste it onto a Word doc. Yeah. Okay, so so we use this. You can use any software of your choice. We just use Primer3, so you can paste your sequences here. So this is traditionally used for picking PCR primers. So by default, you would have the left and the right primer clicked. So you can deselect that and say pick hybridization probe. And you can give a number to return. So I usually give 100, and I think the other parameters are fine. Yeah, it picks an optimal size of 120. You can say pick probes. So this would give you a list. Yeah. So this basically gives you like a big list of potential probes. And what you need to look here is look for probes that end with AG or TA. So the way we want to the way we want to do it is, so you would have a 20 base pair left probe and you have a 20 base pair right probe, right? Based on, okay, let me show you back here. So basically here, so this region is 20 base pairs and this region is 20 base pairs. And there is no gap in between these two probes. They are like continuum of total of 40 bases. And you want AG or TA at this ligation site. So we just use Primer3 to identify where these potential sites may be. Okay. So I'm just going to pick this one, which has AG, so it's at position 965. Go back to the Word doc. So this is basically this is the region which was, so this is the region that was the region that is highlighted in red till AG is the region that was picked by primer 3. So you would keep this and you would add 19 more bases. So that's going to make it a total of 20, and that would leave A and G in positions 20 and 21. So you need a total of 40 bases. So once you have this, you can just paste it onto an Excel sheet. Where's this? Okay. So you can write FGF10, and so you can also like make a note of the NCBI accession number so that you know where you took your sequences from, because in some cases you might have like multiple isoforms. You need to know what you used as a reference sequence, because you usually mention the start site of your probe, and that would change depending on which accession number you took your sequences from. So I usually write accession number here, and then so this is the actual sequence of the mRNA. Your probe is going to be complementary, so we're just going to do a reverse complement of this. So you can use any software and do a reverse complement. So reverse complement. I think I pasted the wrong one. Okay. So you'd have a forward sequence which has AG at positions 20 and 21, and then you would make a reverse complementary. So naturally here it's going to be CT, because your forward was like AG, now it's going to be CT. You would take the first 20 bases, including C, and you would check their TMs, and you would check if these sequences have any kind of hairpins or diamond formations. And once you verify that it has optimal TM and diamond formations, you're good to use that as your edge probe, as your left probe. And you would do the same for the other 20 base pairs, which basically would include T along with these 19 bases. You would again check their TM, check if they have any kind of dimers or self-annealing sites. And once you've checked both of that, you can put that in a part of a template, and you would order that as your edge probe. So I'll go over the entire thing now. So okay, so these are the first 20 bases. Go. And you would say calculate. So these would give you the TMs. So we usually try to keep it between 45 to 65. Try not to go below 45. And if you're working with like probes that have like more A's and T's than C's and G's, then it's really hard to find a suitable region. But usually you should be able to find at least a few probes that would fit within the range of 45 to 65. Optimum is 60, but that's not always possible. So you can, as long as you can fit it somewhere between 45 and 65, you should be good. And the other thing you can do is check self-complementarity, make sure that there are no hairpins or self-annealing sites. So once you know that the TM works and you made sure there are no hairpins, so this probe sequence is good to go. Now you would go back and do the same thing for the other 20 bases. calculate. So you check the TM, then again you will check if it has any kind of self-complementarity. So in this case we are lucky, like there is no hairpins or complementarity, but in some cases you will see that they have some, and if you do, then you have to like look for another probe site. You'll basically go back to the primer tree, look at the list of probes, find another one that ends with AG or TA, pick that, and do the same thing all over again till you find an optimal probe. Okay, so now we have two sequences. Okay, so now we have these two which we think are like good to go. So this is just a part of the edge probe. This is not the complete one. We go back here. So what we have designed right now is just this part, this 20 and this 20. There's an overhang. So that overhang is kind of fixed. So if you were to use site 3, you would pick a particular template. If you were to use a fluorophore that's like in 488, you would use a particular template.
So here.
Yeah, so that's the neighbor probe.
This is like
Yeah, so there is, I think we have.
so the overhang have directly.
I can show you. So this part, basically the one that says template for designing. So if you look at that page which says, yeah,
Very low
yeah,
overhang
yeah,
sequence.
yeah. So that has like oligo sequences, and then I've like written just LLL. So that's where you would insert the left probe sequence, which you now just designed.
L is on left.
Yeah, yeah. I can show you on the sheet how it's done. Okay, so let me see. So the first half of the reverse complementary sequence is going to be a left probe. So if you pick, like say you want to do this in sci-fi, if you look at your sheet, you have this oligo sequence that says LLL.
Yeah.
So you replace those L's with this sequence, with the
Okay.
first half of the complementary sequence.
So
And-
first like it is two piece.
Yeah, you just ordered it as like one long oligo.
Okay.
Yeah, you just take the sequence and insert it into the template. And if you look at the other, what's the other one? Yeah, so this says HL5X gene position. So we are designing for FGF10, so it will be like HL, which is hybridization left. 5X is just a way to kind of like symbolize that it works with Sci5. So in gene, you would write it as FGF10. In position, you would write the start site, which in this case was like 965. So this is going to read like HL5X, FGF10, 965. So that's the name of your probe. And the sequence is going to be basically this entire sequence that starts with like TAG and ends in ATG. And instead of the LLs, you're going to replace that with this. And that entire sequence, you would order it from IDT. And that's going to be like one set of the probe. That's one part of the set, yeah. That's just the left. And you do the same thing for the right. So this is the sequence for the right. You would go back to the template. So here it says HR5X. So you would make it like HR, hybridization right probe. You would write FGF10, position 965, and it already has these R's. You would replace those R's with the sequence that you just found. This is basically this one. Yeah. So here, I think this gene is like smooth muscle actin, and I think these probes have been designed for working in SAT5. And here we've designed it for human, so we usually like indicate whether it's mouse or human. So if you were using mouse, you can use like an acronym like M or something, just to know that these probes work with mouse versus human. And yeah, so this is your entire left probe, and this is your entire right probe, and you would order this from IDT as 25 nanomolar probes. And standard desalting, these don't have to be like super high quality. Yeah, these are not that expensive. The CZs, the circles, the bridges, you usually order them as high quality, so the HPLC might like cost a bit more, like $30 or something more. But the hybridization probes are not expensive. So this is for doing one gene in Sci5. Say if this is a gene of interest and you think that this is like a common marker, you would use it for multiple experiments. It might be worth to have it in multiple colors. So what you can do is you don't have to do the whole design again. So you already found the optimal sequences for probe binding. So you keep those sequences, but use a different template for like 488 or something. So if you go back to this, you have another template for working with 488. So you would take that template and just add these sequences to it. And if you look at the other page, which has like example for designing edge probes. Yeah. So that's a probe for FTF10 in mouse. And the table has like a sequence which is color coded in blue. So that's the probe binding sequence. And I've written down another sequence which includes the template. So this is the complete edge probe sequence, and it has 3 color codes. The one in blue is the part that's actually going to bind your edge probes. I can show you the schematic I was going to. Okay, so here, so the one in blue is going to be this part of the edge probe, which is basically what you had designed to bind to your mRNA. The part which is in red is actually this part, which is going to be complementary to the bridge, right? And the one in green is actually this part, which is going to be complementary to the circle. And if you notice, the probes have been designed for 2 colors, for Sci5 and 488. And if you look at the red sequence, it's going to be the same in both. Like if you look at the left for Sci5 and the left for 2x, which is 488, you will see that the bridge sequences are the same, because you use the same bridge for all fluorophores. On the other hand, if you look at the green sequences for a left probe and a right probe that works in Sci5 versus 488, they are going to look different. That's because the circles you use are going to be different. So that's how you like switch circles and do different colors. So this is just for like one probe set. You would do the same. If you were to design like 5 probe sets per gene or 10 probe sets per gene, you would repeat the same, just find like different regions. There is no logical reason as such, but we usually like place them like 100 base pairs apart, like 90 or 100 bases apart. Like if you design one at like 965, then I would design another one which is like about 90 or 100 bases away from this one, and you kind of like tend to tile the whole mRNA. In cases where you have like very short mRNAs, you can't do that. You can either like reduce the distance between the 2 probe sites, or you can design like fewer probes, like 6 or 7.
And the server will stay in the same pool, in a one pool of probes, right?
Yeah, you'll order them individually, but eventually like you can, so your stops are going to come from IDT individually. They'll be like, for each probe, so there's going to be a left and a right, and you're going to have that like for every probe ordered. But for a same gene, you can put it, so that you don't have to like, if you had like 10 probe sets for a gene, that's 20 tubes, and you don't have to like work with 20 tubes when you're adding or making your buffers.
Okay. And all the probe of the set have the same color.
Yeah.
Have the same color.
Yeah.
So this means that at the end, we cannot recognize which probe will work the better.
No, you can't. You can't unless you do it individually.
Yeah.
Like we tried it individually also. That's when we like realized that some work really well and some just don't work well at all. Yeah.
20 probes are not
Yeah.
experiment.
So we use like 10 probes, 10 probe
Together,
sets.
yeah.
That's a total of 20 probes, but that would be like 10 experiments.
Yeah.
Yeah. So if you were to use 5 probe sets, you can use them at 100 nanomolar each. So together that would be like a total 1000 nanomolar concentration.
Yeah. Obviously, when we use a set of probes, there is no risk that they can cross combine. How can we avoid this problem when we put together?
It could happen.
Okay.
There's like at this point it's like not possible to say whether that will happen.
Okay.
The only things that you can account for is like the probe itself having like hairpins or dimers, but it's really hard to say that if we're going to use like one probe pool versus the other, if any of these probes can interact. But the other thing is we use them at like though it sounds like 100 nanomolar, that is still like really high concentration. So even though it's like some of them might form dimers, there should still be like enough to go and bind your mRNA target. Yeah. Okay. Is this part clear? Like this is kind of like the most important part, like how the EdgeProbe design works. Yeah. So yeah, that's should be it. So if you were designing like 5 or 10 probe sets in SciFi, you would use just the same SciFi template. If you want to swap colors for the gene, then you would just change the template. And when you use Sci3 and Texas Red in the same sample, you might have issues with bleed through. Sci3 and Texas Red have a tendency to bleed through into each other.
Okay.
Yeah. So you need when you image, you need to like image accordingly. Yeah. And what else? Yeah. So I usually, so if I have like one gene, so if I'm gonna do like 4 or 5 in situs, like 5 genes at a time, I usually pick my most important gene in Sci5. It's usually like, it doesn't have any kind of bleed through with any other channel. It's free of like any kind of background issues, and the puncta look really good. So not all puncta would look the same. The SciFi puncta are like super bright and spherical. The 488 puncta, at least like in our microscope, they look a little fuzzy. They're bright, but still like they're not like this bright spherical dots. So I usually like prefer picking my most important gene in Sci5, and you can pick the others. If you have, so if you're gonna try using the 405 channel by like conjugating Pacific Blue 405 to your detection oligo, pick a gene which is like super abundant to work in 405, because at least in our experience we see that the 405 signal is not very bright, and as you store these detection oligos over time, they get dimmer. So as long as it's like a super abundant gene, you should be good.
But normally for example, when I do immunostaining, and I know that the laser 40 that can tell 405 is one of the strongest, that gives the strongest signal.
Yeah, it does. It's just this dye
Okay.
which we have used, like in our experience, we know that the signal looks reasonably okay in the beginning, but over time, when you store these detection oligos, it tends to look weaker. And if you use that with something which is like abundant, then you don't have to worry, because it already has like so much signal, so you should be able to see it. But if it's for some very rare transcript, it's possible you will miss it out. Okay, anything else? Do you have any other questions, or should we just head to the lab?
Just for the initial design, why did you choose AG?
Oh yeah, so this is based on like previous literature, so this is kind of like a 4-way junction. So AG and TA are considered more optimal if you have a structure like this versus like trying other oligos. This is based on like previous literature, like not related to this work, but people have used 4-way junctions before. Yeah.
So you said that your labeled probes get weaker with time? So
Uh,
are you freeze thawing them, or are they?
Only 405. Sci3, everything
Okay.
else is fine.
Everything else is fine.
It's just that this is something that we conjugate on our own.
Right.
So we are not sure if it's like the buffer that we use is quenching them over time,
Okay.
or is it a problem with that.
So the rest of
the
them are
rest are
fine.
The rest are fine for like